Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Production and Carbon-Carbon Bond Formation, Application in Organic Synthesis, taken by Professor Yashwant D. Vankar, retired from Chemistry Department, IIT Kanpur. So, this is our 10th tutorial session. So far, we have been discussing up to we have discussed, I think, up to week 8 lecture contents, and we have discussed the mechanisms of the reactions which are taught by the professor in the lectures, and we have also solved several questions related to that, and we have solved up to week 8 assignment. So in today's session, firstly we will be discussing week 9 lecture contents, and then we will move ahead with the discussion on week 9 assignment questions. So in the last lecture, we have discussed about this asymmetric hydrogenation. One of that was Nola's Nobel-winning work, that is using this type of chiral compounds, that is RR minus DPAM and this COD. We can hydrogenate different compounds. For example, this compound to give this one, which is L-DOPA, a medicinally important compound. And then we have also seen this Noyori's Nobel winning work using binaps as chiral ligand. So this is a chiral binap ligand, binap, that is a phosphine ligand, binaphthyl phosphine ligand. So its mirror image is given here. And this is used also for the isomerization of olefins, which is a very important application in industrial field. So here this is beta pinene. So if we do the isomerization of olefin and some more chemical transformation, we can convert this beta pinene into minus menthol. And here, as we can see, this compound, upon this rhodium catalyzed R-binap condition, it is undergoing this uh, isomerization, double bond isomerization. And if we use one particular binap, we are getting this methyl group above, and the other particular binap, that is S enantiomer of the S isomer of the binap, will be giving the opposite one, that is with this methyl group alpha. Now, if we see this another example here, we can see using this particular catalyst, this alpha beta unsaturated ketone is undergoing hydrogenation, that is reduction of this ketone to form this alcohol, and this is a vitamin E building block, and the chirality is installed by using this particular catalyst, which is a ruthenium based chiral catalyst. And here we can see the bina part is also there. Now, some of the reagents which is used for the enantioselective reduction of ketones involves this NaBH thrice, like chirally substituted lithium aluminum hydride or aluminum hydride, or this boron reagents, or this chlorodiisophenyl camphenyl borane, that is dipchloride. So if we see this oxazoborylidine CBS, that is Bakshi Shibata catalyst, they are commonly used for the enantioselective reduction of ketones. So we can see like this. So this is S-prolin. Firstly, upon treatment with this oxyl chloride, this is getting acylated. This N-acylation is happening, that is COCl is coming over here. Then in the presence of this triethylamine, this oxygen is attacking over this center and this lactone formation is happening. So that will give this compound. Then when we treat with this phenyl magnesium chloride, it will attack over this, it will attack over here first, then H2SO4 and OH minus will cleave this to form this compound. So this is enantiomerically pure, and it is having 99% of enantiomeric excess, which is derived from this S-proline. Then if we treat it with this trialkyl boroxime, it will form a complex like this. So here, as we said, what is happening? Firstly, this phenyl magnesium chloride will attack over this carbon, and it will form this intermediate. Then when this bond will shift over here, this will shift over here, and this will go, and the CO2 will be eliminating to form this intermediate, which upon hydrolysis can give this one. So this is that particular catalyst, that is this oxazoborylidine CBS Bakshi Shibata catalyst. So this is how this catalyst can be prepared from S-proline. Okay, so now if we consider, if we are using one equivalent of BH3 along with this particular catalyst, it can interact with this nitrogen and form this kind of intermediate. Then what will happen? This, when we treat it with this ketone, this ketone, this boron will coordinate with this ketone, and it will form this kind of compound. So as we know, this is the small group and this is the large group here. So when this proton is getting transferred from this corresponding borane to this ketone, this bond will migrate over here, and it will form this particular intermediate. So it will be, this proton will be coming from this small group side, because this binding of this boron with this ketone will be in such a way that steric hindrance, to minimize the steric hindrance, this side which group will be coming, the small group will be coming, so it will give this particular intermediate. So that can again dimerize and form this kind of a dimer, and which upon hydrolysis will give this compound, which is equivalent to this one. So using this catalyst in THF, we can convert this racemic compound into this enantiomerically pure compound with 97% of enantiomeric excess. So this is another example of this enantiomerically pure catechol enantiomerically pure reactions carried out by this catechol borane. So here if we see, we are treating this catechol borane with this type of ketone. So if we treat that catechol borane and this particular ketone in presence of the CBS catalyst, we will be getting this compound, which upon treatment with this NaN3 and this NaOH, firstly this epoxide will be forming and N3 minus will attack over here and this will open up, Cl will eliminate and will form this particular intermediate. Then what is happening, this can be converted into corresponding carboxylic acid, which can be written like this. And then H2PDC mediated reaction will convert this N3 into this NH3 plus, and the COOH will be COO minus, that is alpha amino acids. So instead of BH3, we can also use catechol borane, where BH3 may interfere with the double bond or amide. So this procedure is useful to procure unnatural alpha amino acids. So, for the carbon-carbon bond formation, using the stabilized carbon ions, that is enolate, which are generated by the action of non-nucleophilic, usually base on a ketone, as it is difficult to generate aldehyde enolates because they are too powerful as electrophile or an ester, amide, etc. So here, if we see, there is an alpha hydrogen, so base can abstract this alpha hydrogen because of its acidity, usually non-nucleophilic base. So this will shift over here, and this will become this enolate, which will be stabilized by a metal. So this reversibility of this reaction depends on the acidity of the carbonyl compound and the strength of the base used. So they are ampidine nucleophiles, which means they can react on carbon or oxygen, but this is usually may be controlled to give the desired C alkylation. Now, enolates are just not the resonance stabilized compounds. They really do exist. They are not just resonance form which reflect some of the character of the real species in solution, but they are actually isolated species, and their structures are confirmed by XRDs. So, ampidine nucleophilicity of enolates poses problems like whether O alkylation takes place or C alkylation takes place, and sometimes polyalkylation can also take place. So if we see this particular carbanion, which can be written in this form also, that is enolate. So methyl halide will attack over this and enolate, and it will form this compound. Then again, in the presence of another one, it can form again enolate here, and then methylation can take place again to form this compound. So like this, polyalkylation can take place, or even this can be quenched with this O alkylation could also take place and give this compound. So this is C alkylation that can continue and give polyalkylated product, or this can stop at this O alkylated product also. So that is the one problem associated with this amped and nucleophilicity. So, how we can control this? So, O alkylation is favored by hard electrophiles, oxygen-based living groups, larger counter-cation, and dipolar aprotic solvents. Now, C alkylation is favored by soft electrophile like iodine is best living group, small counter anions like lithium plus is the best, and protic solvent, solvated O minus. So if we see this particular example, so this is an enolate. So either this can get O alkylated to form this new carbon oxygen bond, or it can get this C alkylation to form this new carbon carbon bond. Or another possibility other than this O alkylation and C alkylation is that aldol can happen. That is this can attack over this particular aldehyde carbonyl carbon and form this aldol, that is beta hydroxy ketone. Then if we dehydrate this product, we will get this alpha beta unsaturated compound. So let us now look at the reaction of an enolate with methyl iodide. So first of all, methyl iodide, as we know, is a weak electrophile. So here we said that soft electrophile, C alkylation, hard electrophile, O alkylation. And for the methyl iodide, cation coordination is strong with the enolate O minus as it has greater negative charge density. So methyl iodide will be giving this thermodynamically more stable C alkylated product. But if we use this chlorotrimethylsilane, the corresponding enol silyl ether is formed. This is because this is a stronger electrophile as compared to methyl iodide due to electronegativity difference between silicon and chlorine. So the SN2 transition state will therefore resemble the reactants more than the product. Also, compared to the carbon silicon bond, oxygen silicon bond is very stable, and the reaction would be proceeding via O alkylation thermodynamically. So in the case of methyl iodide, that is lesser strong, like weak electrophiles, C alkylation will be favored, and stronger electrophiles, this O alkylations will be the thermodynamic product. So one alternative thing we can do to prevent this is putting a temporary group to direct the carbon-carbon bond formation and remove when necessary. So for example, if we consider this particular example and we are alkylating this center, that is alpha to this ketone, we will be getting this product. Correspondingly, if we are alkylating the sulfonyl compound and nitro compound, we will be getting the respective product. And then if we remove this ester and this sulfonyl group and this nitro group, we will get the desired product. So here the possibility of O alkylation is less, and we are getting only C alkylated product. Only problem is that installing the CO2 ET or SO2 pH or NO2 and then removal of that will take extra 2 steps. So here it was just simple reaction, that is methyl iodide on enolate, we will be directly getting this compound. But in the case there is a competition between O alkylation and C alkylation, this is one method which we can follow, that is putting a temporary group to direct the carbon carbon bond formation. So another alternative for this is enamine. So if we prepare the enamines, that is this type of ketone is there. First we are converting it into this enamine, which can exist in this iminium ion form also. So what is happening if we treat this with some alkyl halide, alkylation will take place only at this position, and then hydrolysis can remove this enamine and form ketone again. So we can use it for alkylation, acylation, Michael addition, and there is no self condensation. So these are some of the advantages. Some disadvantages of this reaction is whichever alkyl halide we are using, that must be reactive, such as a primary halide or any other living group. Then we cannot use allylic or benzylic, and if Michael accept is there, that is also problematic. Sterically bulky and tertiary also will not react. Now, with unsymmetrical ketones, there is some problem. That is, if we use this particular ketone, it can form either this or this one, where this will be the major one. And besides that, N alkylation is also possible. So, although it is more likely that with more reactive allyl and benzylic halide, N alkylated product may rearrange to C alkylated product. So, if we see here, firstly, this N alkylation is happening. Then, while this iminium ion is forming, this is getting attacked over this position, and then we are getting the C alkylated product, but it is going through this N alkylated product. Now, some application of this enamine involved. So, firstly, if we treat this compound with this alpha beta unsaturated compound, we are getting this one. We will see how it is happening. So, firstly, what is happening? This nitrogen lone pair will fall over here. This is attacking over this position. This will come over here, and this is becoming enolate to form this. Then, when this negative charge will come back, this is getting um, forming this carbanion. Then this negative charge will take proton from here, and it will form this particular carbanion, and then this will attack over this iminium carbon, and this stabilizing this positive charge on nitrogen to form this particular intermediate. So another example is this one. So here also this nitrogen lone pair is falling over here. This is attacking over this this beta position, and then this is coming over here, this is becoming enolate, so we will get this one. Then again it is taking proton from here, that enolate we can write in this ketone form, and this is taking this proton from here and forming this particular intermediate. Then this again will come back, this will attack over here and stabilizing the positive charge on nitrogen to form this mesembrin. Now if we see the use of this enolate for this silyl ether formation. So this enol cellule ethers can be used as directly as weak nucleophile with very reactive electrophiles such as carbonium ion halogens or pseudohalogens, and they can be cleaved by using nucleophiles such as methyl lithium, lithium amine, or this ammonium fluoride salts to give reactive enolates. Now, these are some of the examples for that where this enol silanes are cleaved using this tertiary butyl chloride and TiCl4, where this regiochemistry is maintained, and this tertiary butyl chloride is used for this alkylation also. So here also same thing. This alkylation is happening using this titanium tetrachloride. Here also this alkylation is happening at this position. Same thing is happening here also. This position, this alkylation, and here alternative to tertiary alkylation exists, but it is not as simple nor as clean. So here what is happening? This CS2 methyl iodide is first undergoing alkylation at this position. Then, in the presence of this dimethyl copper lithium compound, it is attacking over this methyl, it's attacking over this position. This is attacking over this methyl, forming this intermediate. Again, ketone will come back. This double bond will shift over here. One SME is leaving to form this compound. Then again, this reaction can repeat and it can form up to this particular uh, tertiary butyl group. Now, similarly, these are some more examples for that. Now, if we see the alkylation via imine chemistry, so from this imine also this alpha proton is acidic and that base can abstract that proton to form this intermediate. So, if alkylation happens, it can give this particular compound, or if this can get isomerized to form this enamine also. Since this M plus prefers to stay close to nitrogen, C alkylation occurs in most cases. Further, here C is soft whereas nitrogen is hard. Now, if we see the chiral alkylation, so firstly, this with this chiral amine, the ketone will form this imine, and then LDA will abstract the proton, and ethyl iodide will be coming from the less sterically hindered phase. So it is coming from only one phase and giving this enantiomerically pure compound. So here a beta chelation is possible. So if we see this particular enamine, when this is attacking over this ethyl group, this iodide is coordinated with this lithium, which is again coordinated with this nitrogen, and this will install the chirality and for this imine, and then hydrolysis will give this enantiomerically pure this compound. Now for the acyclic system also similar reactions are possible, and we can get this enantiomerically pure compounds. Then these are the other examples for this asymmetric alkylation using this particular enamine based compound. So I am not going into detail of that. Now next reaction which we all know is aldol reaction. So that is basically this uh, base will abstract proton from here, and that will attack over this carbonyl carbon to form this one. So either it can form syn compound, that is erythro, or it can form anti compound, that is trio. So mixture of aldols will form syn, and anti aldols have to be separated. Now, this aldol reaction can be directed also to direct the regiochemistry of the product, and we can control the stereochemistry of the reaction as well. Then there are acid catalyzed aldol reactions also, which make use of enol ethers, for example, enol silyl ethers instead of metal enolate. For in that, the titanium tetrachloride is the best catalyst, and using this acid catalyzed aldol reaction, retroaldol reaction is prevented by the stable titanium chelate complex. Now, the disadvantage is that the reactions are non-stereoselective compared to using lithium or boron enolates. Now, the stereochemistry of the aldol reaction, where we can have either diastereoselective reaction, because there are four possibilities. So either syn, anti-syn, erythro, or anti-trio can be formed. So both stereoselectivity and diastereoselectivity have been discussed. Now we will come to the week 9 assignment question. So the first question was, in the following reaction the structure of major alcohol is. So this particular ketone upon treatment with the CBS reagent, then BH3DMS, NaOH, and H3O plus, which will be the major product out of the four options. So if we see this question, so the correct answer would be option 3. And as I said, this is the CBS catalyst. So CBS catalyst, what it will do, it will carry out the reduction of this particular ketone in ensure selectively. So this is R proline base oxazoborylidine, which is a CBS catalyst. So here what is happening, this particular catalyst will react with this BH3 to form this intermediate, and then this boron will coordinate with this ketone to form this particular compound. So if we see, this proton is coming over this ketone and this is moving over here to form this particular compound in such a way that, yeah, so it will be having this particular stereochemistry. So this correspond to the large group over here and the small group over here, so that will be giving this compound. So the correct answer would be option 3. Moving to the next question, in the reduction of prochiral ketone A with dip chloride, that is chlorodiisoprenyl camphenyl borate, the transition state B you have to identify, and what will be the byproduct C you have to identify. So here the correct structure of B is the transition state B is this second one, and C, that is byproduct, is this fourth one. So hydrate transfer happens via a six-member transition state leading to stable tertiary carbocation. So here, if hydride is transferring from this position, it will give to this tertiary carbocation, and if it is from this one, it will give primary carbocation. So tertiary carbocation is more stable, so it will go through this intermediate. Now considering the byproduct, the proton loss from tertiary carbocation will lead to more substituted olefin. So if it is going through this one, it will be leading to more substituted olefin. So the correct answer would be option 4. So B 2 and C 4. So that is the correct answer. Now the next question is the transition state that correctly depicts the reduction of prochiral ketone with the CBS catalyst derived from R proline and BH3 is which one? So here, as we know, the correct transition state from R proline derived catalyst should be a mirror image of the transition state derived from S proline based on a Corey Bakshi Shibata catalyst. So the correct answer would be option 3, as the S proline based transition state is given below. So the S proline based transition state means this one. So the small group is this side and large group is this side. So the mirror image of this one means it will be option 3. So the correct answer would be option 3. Now the next question. R Noyori's name is associated with which reaction? Asymmetric epoxidation, asymmetric dihydroxylation, asymmetric reduction of ketone, asymmetric hydrogenation, or a Korean chemist? So which are the correct options here? So here the correct answer is R. Noyori is a Japanese chemist, and he has developed asymmetric reductions including asymmetric hydrogenation. So the correct answer is option 2, that is asymmetric dihydroxylation, asymmetric reduction of ketones and asymmetric hydrogenation. Next question, the major product that will form in the following reaction. So this particular compound upon treatment with this red dye and copper bromide in the first step, and the second step with LDA, and this chlorotrimethylsilane, and the last step with this SNCACl2, and this particular compound, which will be the major product. So here, red dye, what it will do in the presence of copper bromide, will reduce enone to saturated ketone, which upon reaction with LDA. So this will reduce this double bond. This red dye with copper bromide will reduce this double bond. So red dye will reduce the double bond. Then LDA, being a bulky base, will abstract proton from this center, and it will form this particular enolcylyl ether. Kinetic deprotonation will be happening. Now what will happen? SnCl4 will react with the halide to form this primary cation, which lead to another tertiary cation after this methyl group migration. and then this will attack over this particular carbocation and form this intermediate. Since this ethyl group is above, this attack will be from the below phase, so this will come alpha. So the correct answer would be option 3. Moving to the next question, the major product that will form in the following reaction. So this particular enol ether, upon treatment with this compound in presence of this trimethyl silylotriflate and then tetrabutyl ammonium fluoride and hydrolysis, which will be the major product. So here what is happening? Firstly, the reaction proceed like this. So this particular nitrogen lone pair will fall over here and this will stabilize. This group will leave to form this particular compound. So then what is happening? This enol ether will, this bond will come over here and this will attack over this imine carbon, and we will get this product which upon hydrolysis will give this NH2 here. So the correct answer would be option 1. Next question, the major product formed in the following reaction sequence. So this particular cyclopentanone upon treatment with this compound, then LDA, allyl hydrolysis, and this triethyl lithium borohydride, which will be the major product. So here, this is an enantioselective imine reaction. So firstly, this enamine will be forming, and this will attack over here, and it will form this intermediate. So since this is the reduction, this is reduction will happen from the beta side because this is coming alpha. So the proton will be coming from the beta side, and hydroxyl group will go alpha because this is also alpha. So this will be the corresponding product. So the correct answer would be option 2. Now the next question, identify the product in the following sequence of reaction among the choices provided. So here this firstly with RAMP H plus, then LDA methyl iodide, then LAH, and then Rani nickel, which will be the major product here. So here what is happening, this RAMP will form the corresponding hydrazone, which will undergo alkylation from the beta side since the methoxymethyl chain is alpha oriented. Then the reduction of hydrazone will take place with this LAH will form sterically less hindered alpha side, and then this is followed by NN bond cleavage to form the product which is shown in this 3. Option 3 will be the correct answer. So firstly hydrazone formation, then alkylation will take place, then that will be reduced, then Rani nickel will cleave that to form this imine. So the correct answer would be option 3. Moving to the last question, the configuration of C1 and C2 in compound A given below. So C1 and C2 configuration we have to identify. So here, as we all know this can in prologue in called nomenclature. So when we do it by that, I'm not going into the detail. The C1 stereochemistry will be having C1 will be having S configuration, and C2 will be having R configuration. So the correct answer would be option 1. So this with this we will conclude today's session, and if you have any doubts or questions regarding the today's session, please feel free to ask. The next session will be on next Saturday 5 o'clock. So thank you for joining and thank you for listening. Thank you.